Yeah, so next are dynamic time warping, or is dynamic time warping. So dynamic time warping now allows also at least local stretching along the time axis, yeah, in order to minimize the distance between two time series. Yeah, and it also allows comparison of time series of different length, of course. So yeah, possible applications are, for example, you want to compare hummed songs where the time is not absolutely synchronized, and well, some hum it a little bit slower, some hum it a little bit quicker. So then you may need to use some local stretching, some local alignment of along the time, and then dynamic time warping can be very interesting. Yeah, handwritten documents, biometric data, and stuff like that. So those applications typically use dynamic time warping to compare time series. Yeah, and here's a comparison between Euclidean distance and dynamic time warping. So Euclidean distance, you just compare each time slot to the same time slot, yeah, obviously. And with dynamic time warping, you can compare one time slot, for example, of the blue one here, one time slot of one time series to multiple time slots of the other time series. Yeah. So here, for example, this one here is compared to 1, 2, 3, 4, 5 of the red one, yeah, and 6 even, yeah, and then that's what you can do here. And you can see that here again. So the lines here indicate the matching of the time slots here. Yeah? And you see that you can have some stretching, some warping. That's why we call it time warping. Some warping along the time axis. So you can do the time warp here. Anyway, so here is the formal definition, a recursive formula which looks very similar to the edit distance. Actually, it's the edit distance, but that's a different story anyway. So given two time series can be of different length, as you see here, and we also need a ground distance, like in the general version of the edit distance. Then we have this recursive formula. So if the time series are both empty, have no values, then it's 0. If you compare one x here with an empty one, then it's unendlich, infinity, in both cases. And the other one is, okay, you just compare the last thing. So you once again compute the whole thing, or you compute the whole thing from the last time points. So you compare the last time points with the ground distance plus the minimum of shifting both, just shifting one y or shifting x. Yeah? So it's very similar to the edit distance. No, it's actually the edit distance. Yeah, but anyway. Yeah, time series are typically real values, so the absolute distance L1 is very often used as a ground distance. So in that case, it's just, so this delta here is the ground distance, just L1. And one of the most prominent variant of dynamic time warping is using Manhattan distance. So this one here as the ground distance, and then for the P here, 2. Yeah, so you square that and take the square root again at the end, which ends up in something like the Euclidean distance, basically. Yeah, but now, so it's similar to the Euclidean distance, but you allow time warping, yeah, for the Euclidean distance. That's the basic difference, or the most important difference, actually. Yeah, so dynamic time warping computes the alignment of two time series, yeah, and that alignment is represented by a warping path of the indices. Yeah, so the warping path has some indices, yeah, like here, which consists actually of pairs that you compare. So you compare one value from x and one value from y in each of the indices here. Yeah. And those time slots or those values from x and y here in those pairs can be from different time slots. That's the most important point now. And now there are some very important properties of this warping path here. First of all, the boundary condition means that it starts at the beginning in both time series and it ends in the last time slots of both time series. Yeah, so it starts with the first time slot in X and the first time slot in Y, and it ends with the last time slot in X, that is N here, and the last time slot in Y, which is M here. Yeah, so that is the boundary condition. The monotonicity states that we have no movement back in time. So so this is the consecutive, or this is the previous time slot to this one here. So if you take the minus here, that's greater or equal than 0. So you either remain from one. So this the PTs are those indices here. Yeah. Or those indices here. So either for X you stay from one index in the path at the time slot you are, or you go one further, but not back in time. And the same for Y actually. Yeah? Continuousness says that no time slot is missing, so you don't. The step is always at most 1, at least 0, at most 1. Yeah, so you don't miss any time slot in X, and you don't miss any time slot in Y. Yeah, so yeah, you see here that, for example, so in that case you would miss this one here, or you will go back in time. From this one to this one here also. That's not okay, so to say. Yeah? And then there is a length bound in P. Yeah, so the length of the warping path is something between the maximum of n and m and n plus m plus 1. Yeah? So those are the properties of the warping path, the same holds true for the alignment path of the edit distance, basically. Yeah, so how to compute that? Well, let P denote the set of all paths, warping path that satisfies those 4 boundaries. The size of those of the set is exponential in n plus m. Yeah, like we know it from the edit distance before. And now let the cost of the path between 2 time series be defined as the ground distance is L1, and then we take P 2, so the whole thing is squared. So let the path be the squared differences of each time slot, or time slot that is compared in the warping path. So then this one can be so the DTV can be defined as the path with the minimal cost here. Yeah, so the DTV dynamic time warping distance is the cost of the minimal path of this of the minimal warping path here. Yeah, for the time series with the same length n, the warping path has the length n. Or the warping path, the warping path that has the length n yields obviously the Euclidean distance, because in that case we can only compare each time slot of X with the same time slot in Y. Otherwise, those 4 properties will not hold for this warping path here. So there's basically no warping in that case.